webinar, we'll start with a discussion of Wireless InSite's capabilities in general, and then move on to the new capabilities, the mobility features, broadband simulations, hybrid EM using full wave to ray tracing, using Huygens surfaces, and lunar propagation. At the end, we should have some time for questions. You should see a panel similar to this. There's a question section which can be unlocked, undocked, and expanded. You can enter questions there. We will look at those and I will answer as many as I can during today's talk. Anything that we don't get to, we will be able to answer you afterwards in the next day or two. So please, we look forward to seeing what kinds of questions are being asked and what people are wondering about. Wireless InSite capabilities. Wireless InSite is part of Remcom's suite of products. Remcom has been producing software for over 25 years, starting with its flagship product, XF-DTD, a full wave solver, used for all sorts of things. Wayfarer is one of our newer products, which is used for radar sensing, RCS, etc. And then Wireless InSite will be the focus of today. Our 3D GPU ray tracer, useful for mobile platforms, broadband propagation. It's HPC enabled, and we'll overview some of those capabilities. Wireless InSite includes a suite of propagation models for comms and for it enables you to run MIMO, SISO simulations, calculate throughput, and other MIMO beamforming techniques as post-processes. The model X3D is validated up to 100 gigahertz. It's GPU accelerated, used for complex urban or indoor environments, long-range propagation, and models, realistically models the material properties, including diffuse scatter up through millimeter wave. Outputs include detailed path data, CIR, complex impulse response, etc. The path data can be used to for channel emulation, for synthetic data, for machine learning, many applications. Wireless InSite is sort of agnostic to the scenario, useful for all these different kinds of scenarios. You define the geometry and the material properties, the frequencies you're interested in, the antenna patterns you're interested in, and Wireless InSite will do its job. Going on to the new features, Wireless InSite Mobility allows you to create dynamic scenarios and simulate how movement of devices, vehicles, people affect multipath coverage of wireless systems and communications. Mobile platforms are assemblies of objects and or transceivers and let you move them through a scene, maintaining their physical relation to one another. You can visualize the multipath in the scenario. You can plot versus time, looking at how shadowing varies over time, how fading is impacted over time, how link performance is affected over time. As typical with Wireless InSite, at each time step, you have your full set of outputs, including your path data. Any of the requested outputs will be available to you for every single step that's been simulated. Mobile platforms are defined by positioning transceivers and transceivers and geometry together. There's a panel for seeing how those two are related. Each can be adjusted independently relative to what we would call the origin of the platform. This allows you to see how things are placed. You can bring things in together, migrating them from a static scene. And once you have the objects oriented relative to one another on the platform, you then can define their movement through the geometric scene. This is a 2D down view of the geometry, which allows you to graphically define the waypoints, but you can also do that more numerically, which I'm showing you here. So the platform editor allows you to see the configuration of geometry and transceivers. You view the waypoints in the geometry view, but you also have a panel where you can define each waypoint numerically. And waypoints include the XYZ coordinates and the roll, pitch, and yaw. You can also decide that you would like to define a time-based waypoint. What I'm showing here is the constant speed trajectory. And so you'll see the speed is defined here. Right now, I just have it at 0. Obviously, that's probably not what you want. But if you choose time-based waypoints, you'll have a next column, one more column for time, and you can define where and how that object and that configuration of transceivers and objects is moving through the scene at each time step. That would enable you, for example, to have something that's rotating. You wouldn't have to have changing waypoints. You could just have rotations. It allows for very flexible definition of what kind of movement or change in time that you'd like. You also have an option to define the exit condition, which has 2 options at the moment. You can the platform can remain in its place and just basically park and stay throughout the rest of the simulation. You might have multiple platforms moving, and one might just come and stop and stay where it is, or you might want it to just vanish. You might want it to just leave the scene, not be there anymore. So you have some options. Wireless InSite under the hood is then has to know, well, when do you want to sample this? What sampling rate would you like? Because a simulation will be made at a fixed rate. And this is then a study area property. Anytime you're setting up a simulation in Wireless InSite, you're defining a study area. Here we have X3D. This mobility capability is a X3D feature. So you have X3D as your model, and then you have your usual inputs of how many reflections, transmissions, diffractions. And what you have new here is the mobile platform time interval, which is defined in seconds. So this is telling the engine, I would like to sample my scene every second, and that's what we will do. We will figure out exactly where that platform is, all the antennas, the rotations of the antennas, positioning of the object as they are related to each other in this scene, and run a simulation for each of those steps. Prior to running, you most likely would like to see how many simulations you're going to be running, and maybe want to see, well, where is this thing moving in my scene before you actually run. And that's done through the platform tab, where you have a panel that looks like this, and you can choose to view the platform's movement, or all the platform's movements, based on the time sampling defined in any of the study areas. So this drop down would include any of your study areas, as well as the option to define your own sampling rate. So you might want to say, okay, well, in this study area, this will turn into 6 steps. That means I'll have 6 simulations. And then you might want to check your 1 second sampling rate study area to see what it would do. And maybe you want to just run 50, and you really don't care how many you're running, or you really need a tight sampling rate. You can plug in before you decide what you're going to run in your simulation. I have an example here of plotting versus time. prior to this, I think it might be useful to actually show you how this works in an actual scenario. So I'm going to escape here and show you just a scene. This is just a small urban scene, and it's hard to see now, but here the platform is the platform panel I was talking about. So let's look at those two platforms I have. One is a person with a UAN antenna, a user-defined antenna. This is based on measurements of a wideband antenna. The scenario is someone has an ultra-wideband phone app where they can find their car, and they're walking through the city trying to communicate with their car. And you're trying to decide, well, how well does this device work in various environments? So and how does it work when there are other things going on in the environment, like buses and trees and buildings? So that's the example we're looking at. We've brought in a person with its handheld device antenna, and the waypoints are defined here graphically, but you can also view them here. And as I mentioned, this is just XYZ, roll, pitch, yaw. If you'd like to edit in bulk, you can do that. It's easy to just bring in either a text file or edit in bulk like that. I've defined another platform that's just a bus, a city bus. It moves through the scene at a varying rate. And so I use time-based waypoints. Time-based waypoints as well. So you see for each time step in this last column, I have where the bus is. And if we want to preview what's going to happen, I can use this drop down to decide, okay, I want to see the sampling rate of 1 second, and I can step through and see what's happening in this scene by just viewing this like we're looking now. It's hard to see the little person in here, but there's a person also moving. You might be wondering what this bus is, but it's my results, I think. So I'm just going to show you now what we can do in terms of results. Stop that. So my study area, I had 2 different study areas. So sampling every second gives us more time steps, and it looks a little more interesting. We have a new results browser. So along this set of tabs, we have a results browser. This is set up very similar to what you'll see in XF, DTD, and in Wayfarer, where you have simulation. Excuse me here. Excuse me. You have your simulation, you have your transmitter, receiver, results. And we're looking at paths. We're interested in paths. We're going to view paths in this scene. When we do that, the results viewer window comes up and shows, it looks like this. And it has controls that let us look through the scene for every single path. Pull that back a little bit and let you see how these paths change over time. So as the person is moving towards the car, you can see the paths at each time step. You can see the interactions with the bus. And you can see what the paths are interacting with. This can be scrolled, as a loop, or it can be or you can stop it and step through it step by step. Excuse me. All right. Going back to the presentation. As I was saying, this allows you to also plot results versus time. In this plot here, you can see time on the x-axis, received power on the y-axis. It's just showing the same scenario I just showed you for two cases. The red case shows you what I was showing you, where there's a pedestrian and the car transmitter, that link, with the bus passing by, and you see how it's blocked. There's a big drop here. And without the bus, ran the same simulation, but I did not include the bus, and you see there's no fading. The new results browser also lets you plot versus time, versus TX point, versus RX point, all depending on what your data really holds. If you have multiple frequencies, if you have multiple transmitters, you can decide how you want to view or plot your results. So this again shows you what I showed you through the UI. You have controls to view the path results. Those path interactions can be analyzed visually to start with if you're interested. And then obviously the path files are there for you to post-process or use in an emulator or any other application you wish. For multi-frequency broadband simulations, some of the new features we have are better definition of materials, multi-frequency antennas, which allow you to either have MIMO or SISO antennas, where the pattern is defined for multiple frequencies. If it's a MIMO antenna, you can have multi-frequency S parameters. And both of those, you know, all of that works together automatically when you're running a simulation. If you have a frequency sweep, then the appropriate antenna pattern will be chosen for either part of the link. In addition, we have the multi-frequency materials. So that's new. Now you can define multi-layered dielectrics that vary with frequency. It's a tabulated format, and you can define a surface roughness, and you can define the EM properties of that material as it varies with frequency. We've always had the frequency-based antenna atmospheric effect in X3D. So with oxygen and water absorption, those effects are taken into account automatically based on the frequency you're running. All of these things enable you to, with one project, have something that can be run over multiple bands, which it really simplifies the project and the workflow that you're using. The second benefit to this is the optimization of the run times. If you run a frequency sweep, you ray trace once. You find all those paths. You do not have to recalculate the paths. What's done is the fields are calculated per each frequency, and then appropriately summed, and the powers, etc., gains are calculated for each frequency. The great benefit to this is that you have your accuracy, better accuracy, since you're using the appropriate material definitions, the appropriate antenna patterns, a simpler setup, and then a big reduction in runtime. REMCOM also has a broadband analyzer post-process utility that's not sold with Wireless InSite, but it is available, and it allows you to calculate frequency spectrum and broadband CIR. Multi-frequency antenna patterns, often they will come from measurement or a full wave solver. So this example that I'm showing, these images here, we're running XFDTD for a simple little MIMO array over a large frequency band. And you can see how those come in. There's a lot of definitions. If you clicked through the UI, you would see the pattern changing for frequency and of course changing for each element as well. The wonderful thing is you don't have to have, you know, so many transmitters. This is all defined as one antenna, and the engine will find the correct patterns to use for whatever frequency you're running. So you can import directly from XF, and there's a very simple format for bringing in antennas like this. In addition, like we mentioned, you can have S parameter in a touchstone file format for bringing in as well. Yep, atmospheric absorption, which I mentioned, captures the peaks at 22 and 60 gigahertz. And we actually have it valid up to 1 terahertz. The multi-frequency materials, as I said, there's a tabulated format for these. This is showing you concrete from 1 megahertz to 100 gigahertz. And so there's a long table with the permittivity and conductivity for each of those. That's a single layer though, and you can have even more complex materials. We have predefined many materials, typical materials for ground and buildings that are based on IP recommendations, and those are built in now. So the user has access to multi-frequency material definitions already and does not have to look those things up. For frequency sweeps, that's defined in the waveform panel, and there's 2 options, just to find the start frequency, end frequency, and the count, how many steps you'd like to take, or conversely, defining the start, the increment in your step, and then the count. And the waveform panel will then show you basically the base frequency, and then as well each of the steps that you'll take. There's a little bit of a preview there. Here's an example of a multi-frequency scenario, connectivity in a home, and I just have a route of receivers down here. You're seeing it flicker because it's showing how the powers change as we went through this frequency sweep. All that data is there and available to you. As usual, power, the paths, all the typical outputs you would have asked for in a normal simulation. And then plotting allows you to really sample the way you want to. You might want to just plot specific frequencies. So this top plot has 2.4 gigahertz, 5, and 6 gigahertz for this same receiver route, downstairs route. Then I'm plotting over the receiver point. You also have statistics you can aggregate. You can define, say you want to plot the mean or the max. You can do different kinds of analyses on the data before you plot. And this is mean, max, and minimum overall receiver points. And then this bottom one is for a fixed point, plotting how it varies over frequency. So this is much richer ability to analyze your data and graph it than we've had in the past in Wireless InSite. Hybrid EM is I'll show you how you can simulate full wave 2 ray tracing using Huygens surfaces. So this work was based on the Huygens equivalence principle and the Lorentz reciprocity theorem. And what we do is we use the tangential components of the E and H fields on a closed surface in the full wave solver to find the power transmitted from either a TX or an RX that's represented in here out into a larger environment. So for example, you may bring in a CAD for a smartwatch That includes the PCB, the antenna, the structures of that watch. So here you just have your antenna. In a full wave solver, you would be using all that geometry, all the material properties of that small scale geometry, plus the geometry and physical properties of the arm it's right next to simulate in full wave what's going on, all of the near field interactions, everything that's physically present inside this volume. And you capture, Huygens surface, those fields. Those fields are then able to be brought into Wireless InSite and used in the ray trace. Just an illustration of this, XFDTD allows you to capture the near field effects on the Huygens surface. You bring those into Wireless InSite, and you can simulate a much larger environment. Not only do you have the ray tracing capabilities to do that, but you also, it's going to be much more efficient in terms of the resources you need, as well as being able to be run as a frequency, over different frequencies, etc. Of course, you need to have run your Huygens surface as a multi-frequency if you're doing that. But in any case, you can apply this same watch, this person with a watch on his hand, to different scenarios. You could put them in a room, you can put them in a city, for example, with a GPS, or you could define multiple Huygens surfaces on a single person and look at on-body propagation, Huygens to Huygens. All within Wireless InSite, though, because now in this case you are looking at the interactions with the body that are outside of those near field regions. Wireless InSite does have a seamless interface with the XF creation of these Huygens antennas. It's the Huygens package import. So in XF DTD, you will generate your scenario. You'll have your CAD. You'll have your Huygens sensors, and you'll capture those fields. And then you can export the geometry. You can export whichever results you care about that you would like to bring into Wireless InSite, and you can bring them in as a single package. And that allows you then to define them using the platforms that we have for mobility as a coherent set of data, a geometry and associated antennas. You don't need to move them around, and that's one thing about these platforms. They can be used to move things around, or you can have just things in relation to one another, which is what we have here. So the first picture here is the XF simulation with the fields that are calculated, and then the antennas are brought into Wireless InSite with the geometry and the materials, and then they're put in a scene. And this is a very simple scene, but you can see, okay, how are these rays interacting with some geometry that is no longer in the near field of these antennas, to move from one antenna to the next. So this hybrid concept here allows, for example, chip or device analysis, system performance, to be done in a much larger or complex environment. Here's an example, similar scenario of a person with a watch. And we've taken that now and put it in a city scene. The person is walking about 60 meters down the city street, and we have a GPS plane wave shining down into the city. How do those paths change? Well, there's all sorts of interactions throughout the city, really all through the city. You can see that on the left. And then how does that energy actually come and interact with the person as it moves, as the person moves through the scene? You can see there's interactions with the body, and then there are those paths that interact with the body are entering this Huygens surface from different angles, and that is then capturing the near field effect of those same rays that are moving through the city. Here's just a quick example of how different poses, same watch, same wrist, but different poses of a body through a city will affect the results as well. Receive power here, orange and blue representing the what time is it pose and the walking with the hand back pose. And you see over time how both the power and phase are changing. The benefits of the Huygens antennas. This workflow captures the accuracy of a full wave solver like XFDTD, while also using Wireless InSite's ray tracing, the powerful ray tracing that lets you use optimized GPU ray tracing for a large urban or outdoor scene or indoor scene. It also allows for on-body platform antennas to be simulated for an electrically large scene, for example. Projects that would be too large to run in a full wave solver, you can now run using ray tracing. This decreases the hardware requirements for the simulation and also reduces the run times. For lunar propagation, Wireless InSite allows import of the Lunar Reconnaissance Orbiter LOLA terrain data sets. It accurately transforms the coordinates of RF mobile systems on the lunar terrain. It sets appropriate defaults so that there's no atmosphere in a lunar scenario. So when Wireless InSite senses that you are using lunar data, when the reference sphere is no longer Earth, it's the moon, then the temperature, pressure, humidity are set to 0, 0, 0 vacuum automatically. And then we have a built-in lunar materials database. So importing lunar terrain, it uses the GDAL importer. We now support additional terrain elevation formats. And we also have the ability to view the metadata that is part of that data set. So when you use the importer, you will see the metadata on this side here. You might look for some keywords like moon 2000, what spheroid is being used, things like that, just to confirm, or various things that could be helpful to your understanding what data you have. If the projection is well defined in that set, the importer will automatically set the ellipsoid to GCS moon 2000. If that doesn't happen, sometimes you will have data sets that don't include that. You'll have this projection override, and then the drop down becomes active, and the user can say, I am on the moon, even though my data set didn't know I was on the moon, I'm on the moon, which makes sure that those projections are done appropriately. And then you will notice from this image probably that you do see the curvature of the moon. The transforms are made, and the representation of the moon lunar surface does show you with its the project origin will be at the center of this, and at the high point in the center, and then you'll have your latitude and longitude defined as you'd expect for the moon. The lunar surface materials model the regolith and bedrock for a range of inputs to the models that are defined in the ITU working document, the lunar permittivity document here. So we used this to predefine a set of lunar materials using 21 frequencies, 3 regolith depths, and 3 metal composition percentages for the titanium and the iron. All these different inputs led to about 189 materials, and those are part of a database that's available to Wireless InSite users. As with most import capabilities that we have, bringing in a geometry, you can have a default material. So when you bring in lunar geometry, the default will be one of these materials, and you can change that and define it as you wish after the fact or as your default. Lunar propagation has proven to be quite a little different, or maybe certain things become more important than they are typically on Earth. Just the ruggedness of the terrain, the depth of these craters, and the interest in propagation into craters means that we really are very interested in 3D propagation, not just a vertical plane. You might come in here and really bounce around before you get to a receiver. This top left image here shows power and just a sample of paths between transmitter and receiver. And this shows delay spread actually, and you see how high the delay spread can get. And this is because of all the bouncing paths in this crater. We can look at just an example of how these paths vary as you go through this. This is just showing you paths per receiver as you move through this crater, cross section of the crater. So you see there's quite a bit of variety in where those paths are bouncing. This scenario is slightly different from that, but there's a lot of stuff bouncing around, and that makes us very eager to really get this right. There is ongoing research we're doing now to improve these models, but you are able to run these simulations now with Wireless InSite's X3D model. For longer ranges, you can use vertical plane, but we're working on much better simulation capabilities with a new improved X3D simulation engine. Okay. Ongoing support for the NASA lunar Artemis missions. All this lunar capability is compatible with mobility and Huygens. This can be relevant for communications, you know, with rovers or between a rover and perhaps an astronaut as a side link, etc. So yes, as I said, this work is ongoing to better capture antenna performance while it's mounted on a backpack. All those things are work that's ongoing. So in summary, just Wireless InSite, it's a validated deterministic set of models for RF simulation in arbitrary environments. It's accurate, it provides accurate, detailed path data among all the other outputs that it generates. The new mobility capability allows you to define motion for configurations of objects and transceivers and generate the time-based results per path, per step results. Multi-frequency broadband analysis allows you to define a single project that will be valid over a wide range of frequencies. It also allows you to run optimized frequency sweeps for multi-frequency analysis. The Huygens antennas give users a way to achieve near field accuracy of full wave solver with the ability to run large complex environments that the ray tracing gives you. This improves runtime, requires a smaller resource footprint, and can give you a solution that doesn't grow with frequency. Runtimes don't grow with frequency as much as they would if you were trying to do larger and larger scenes with a full 3D model, I mean a full wave model. And lunar propagation gives you the terrain import and lunar materials database so that you can define the lunar environment, and it gives you the optimized and enhanced ray tracing that you need for lunar environments. Thank you for coming.